In backyard DIY, once students have used the color tiles and collected the data in the unplugged context, they then move on to look at this Scratch code, which essentially does the same thing. And so when students get in here, they click the green flag, and as we can see, the models are being built, and as they are built, the data are added to the three tables of values here. And the question pops up if you want to graph the blocks added, press B. So I do that, it creates the graph. Click P to see a graph of the perimeter. There it is. And click T to see the total tiles. There we go. So that is the code, and there isn't really much for the students to do other than to use it and look at it and analyze different aspects of it. And of course, in the lesson, the teacher is kind of asked to have students sort of analyze what is happening over here and link it up to what is happening over here. For example, you will have created the algebraic expressions for the three patterns. Where are they? Well, here they are. Side length times 2 minus 1, side length times 4, and side length times side length. So that would be like n squared, 4 times n, 2n minus 1. Those are your algebraic expressions. And you can go to the different parts of the code, and you can see here that there is a create tile models algorithm somewhere. Well, there it is, and you can go over here and analyze, well, what exactly is happening in here that allows us to end up with all of this. Now, this conversation is important because when they move on to the second part of the lesson, when they are dealing with the staircases, they are expected to create a code that will build the staircase models, fill in tables of values with the appropriate data, and graph those lines as well. Probably the most straightforward way to do that is to just remix this code and make whatever changes are needed to come up with the difference over here to represent the staircases. In this code, one of the things that I like about this is that the procedures, there are 4 basic procedures. There's the procedure to create the tile models over here. There's the procedure to add data to the list, which is here. There's the reset procedure, which makes which erases and resets everything so that you can use the code again. And then there are 3 blocks here that create the graphs for each of the 3 patterns. There are the other 2 up here. Okay. These procedures have all been abstracted to their basic parts, their essential elements, and they are tangible, meaning that students can manipulate them. They can be manipulated by other blocks. And also within the Scratch environment, they are automated. So students can manipulate these pieces and then run them as many times as they want. And it becomes very efficient to do it that way. The result is that when you're coding and you have the combination of tangible abstraction and automation, you end up with a setting where it is safe and efficient for students to experiment and to look for answers to what-if questions. It's very easy in this context to say, well, I wonder what would happen if I changed the side length, multiply side length by another number. Or if I change some of these values, what happens if I make a change over here? What would the result be? And it's a very low-risk question, because even if the student changes something here and they get something here they don't like, they can just go back and revert the change, and they've lost nothing. So this is different. This is very different from traditional pencil paper work, where students can spend a long time working on something and find out that they made a mistake maybe in the first 2 or 3 steps, and they can't go back and change it as readily. In the coding environment, because of the abstraction, the tangibility, and the automation, you can. So it's a safer place to ask those what-if questions and go off on a tangent, even if it ends up being not where you want to be, incorrect, off topic, you can still bring it back very easily. Okay? And to me, this has something to do with resilience. Now, a lot of the literature talks about how students who code and use computational thinking develop an acceptance of failed solution attempts. And on one hand, that's because the general wisdom is that when you start writing a code, unless you're very lucky or you've done it for years, your code doesn't work as you want it to the first time. So everybody just accepts that. I'm going to make a code, I'm going to run it, it's not going to work, but then I'm going to tinker with it and it will work. But more recently, I've thought about tangibility, abstraction, and automation, and what I've realized is that failed attempts in a coding environment are not as much of a big deal precisely because they can be reversed very easily. So students can ask what-if questions knowing that, hey, if I get it wrong, that's no big deal. I'll just reverse it. I'll admit I was wrong, and I'll reverse it, and I'll go in another direction, which may be closer to being right. So in this environment, students are able to, and are more comfortable to fully try things which very well may be wrong, things that they might be afraid to try in an unplugged setting, knowing that, if I get this wrong, I will have wasted a lot of time, or I'd be further behind than everybody else, and I won't be able to catch up. It's much more forgiving in the coding environment, and so students know and understand that they can ask those questions and investigate those questions, and the stakes are very low. So that's another advantage I see with using coding and computational thinking with mathematics.